AP Stats. This is about try number 6 of recording this. That I've had just a lot of technology weird issues, but I'm hoping that this goes better. So starting linear regression. This is called this topic is the least squares regression line that you see here, and we're going to learn how to fit a line to data, how to make a line of best fit in a statistical method, not just kind of guesstimating it. And it's going to start off with some theoretical things. So you're going to start off with why is a line of best fit a good thing, and then how we judge it. You know, what's the standard by which you judge them, and then what does least squares mean, and what does regression mean? You know, all these different terms that they throw in, and what does correlation have to do with it? And so we're going to talk about these theoretical things, and then eventually from that we'll get the formulas and we'll get the method. We'll get how to find a line of best fit. Yeah, I wanted to give you a quick example. Of why we're doing this or something, and so I thought of the this example in the book. It's you're either buying or selling an F-150 truck, and it has 90,000 miles on it. And the question is, what's an appropriate price for an average Ford F-150 that's got 90,000 miles on it? And the problem is that none of the vehicles in our sample have about that many miles driven. There's 70, 75, there's over 100, but there's nothing at 90. And so how do you make a fair guesstimate of what the best price should be for an average truck of this kind? And I hope you can see that having a line would be really helpful then, because you'd have a formula for it. You can see the formula right here on the line. And so you'd have a formula, so you could use that, like with a line of best fit, you could use that to say, okay, on average for any given X value, like 90,000 miles, then we can predict what the Y should be, so that it gives us a starting point, at least for negotiations at that point, depending on the car. So that's why having a line is better than just having the data. And so we're gonna have a way to figure out that line of best fit. All right, oh, wrong, sorry. Back to OneNote. Forgot I was doing OneNote, not Word. Okay, so so now we're going to scroll down. Sorry, apologize. There we go. Okay, so here's how we're doing it. So the line of best fit is called the least squares regression line. So you can see that down here, and that's the big terminology for what the line of best fit is, and we're going to explain why it's called that now. So here's actually the shoe size data that people sent in, and you can imagine a line of best fit going through this data. I don't know, maybe something like this. You might disagree with my line and say my line's bad, and it's not. Actually, I do know ways the proper line is different, but at this point we're like, that kind of fits the data, you know. And so, so what makes a line good? Well, the best line is the one that minimizes the misses. So it's minimizing how much it's missing by. But specifically, that's how far the line misses each data value. Sorry about that. In the Y direction. So if you kind of think of it, what the misses are is it's this little distance right here, or this distance right there, or that distance right there. It's how far each point is off of the predicted line. And the points aren't misses, it's just those are spots where the line estimates what the value is, and for some reason that data point doesn't happen to be on the line. In fact, you usually won't be on the line, right, as you can see. So this miss has a vocab term, and it also has a formula, and it's called a residual. The residual is how much you miss by. And the way you calculate it is you do the actual Y minus the predicted Y. Actual Y minus predicted Y. There we go. If you need to remember which one minus which one, you will notice that the initials are AP. Cute. So, and there's actually a way to write this symbolically. The actual Y values will write the letter Y. And to write predicted Y, when it's not an actual Y value, but it's just a Y value that our model suggests might be a good Y value or an average Y value for that particular X value, then the way we write that is kind of funny. You write it with a little caret on top. With a little, let me make it a little better there. Actual y minus y with a little like that on top. And that's actually called a hat, like a little cap. And so we'd call that y hat right there. It's a funny thing, but that's just predicted y. That's all it means. Yeah? So we're trying to minimize the total misses. So the line is too low sometimes, too high sometimes. What does that tell you about the residuals? If you do actual y minus predicted y, and I'll give you a chance to see that. And why can't you just add them all up? Add up all the residuals. Give me a second to think about that. And if you think about it, what the problem we're going to run into is that some are going to be positive and some are going to be negative. And when you add them up, then they'll cancel each other out. You can see that you could have a line that doesn't fit the data, but the sum of the residuals is 0 on the nose. And it's obvious, well, that's not a very good measure. And so the problem is that some are positive, and some negative. You might take a second to think about, negative, about which ones would be which. Since you're taking the actual y value minus the predicted, if you're above the line, your actual will be bigger than your predicted. And so you'll have a positive residual if you're above, and you'll have a negative residual if you're below. So just something to keep in mind. So some are positive, some are negative, but we want to add all these up. How do you think we're going to solve this problem? And if you think back to earlier in the year, you go, I bet we're going to take the residuals and we're just going to square them, right? And that's exactly what we do, just like standard deviation. In fact, there's a lot of connections with standard deviation here. And so explain then what least squares means. I'm just going to say this one out loud, that the least squares regression line minimizes the sum of the squared residuals. It's got the least total amount of squares, like if you count the squares as values, the least amount that you could have. That's what makes the line the best fit line. Okay? And so remember we said least squares regression line. Now we know why they call it least squares. But there's another word in there. There's regression, and that didn't help with regression at all. And so, what is this? And this can be like a little theoretical discussion. Don't know why I can't get rid of that. Oop, now I can if I remember where the delete button is. Sorry about this. You can tell my standards have gone down because I'm willing to have that, on the video. So now we're going to explain regression, and it's going to help us understand the formula to find the equation of the line. So the mean height of girls at Seattle Prep is 5'6" with a standard deviation of 3. How do I know that? Because I say so. Suppose I told you we randomly picked a female student. What would be your best guess for her height? You go, well, it's just a randomly picked student. You say randomly picked student. You go, I don't know. Well, 5'6" seems like a good idea. Just guess the mean, and that would be the best guess you could make. Suppose I told you, oh, wait, hold on a second. I'll give you some information. And you go, oh, okay, I take that back. I say, this girl has one sibling. That's not really very helpful, and you'd still say 5'6", right? That doesn't give you any information. 5'6". That still doesn't give you any information that would make you change your answer because, oh, she's got a sibling. That doesn't mean anything. Suppose I told you the girl is one standard deviation above the mean in height, but if you measure in centimeters, what would be your best guess for her height in inches? You say, well, she's one standard deviation above the mean in centimeters. She's going to be one standard deviation above the mean in inches. It doesn't matter what units you're using. It's going to be, that's where she is in the distribution. She's one standard deviation above the mean. It doesn't matter how you measure it. So your guess would be 5'9". All these are totally intuitive and totally correct. So the problem is all these are extreme examples. Either the correlation is 0 or the correlation is 1. So correlation is 0, siblings in height, or about 0, and the correlation is exactly 1 if you measure height 2 different ways. And so we want to say, well, what if you had something in between? And we could use shoe size, like we talked about before, but I decided to go a different one. I said, well, let's use a different context for a second. I'm sorry, from an earlier try that failed. I have a couple of things to erase there. I just got one more. I can't help myself. Uh, yeah, yeah, yeah. This is not going to be a public video. All right. So, Major League Baseball. You've got preseason win percent and regular season win percent. And the thing, if you don't know baseball, is that in the preseason they have a ton of extra players who aren't going to be a part of the team. So just the fact that they're preseason games, and so you're not ready to play the regular season yet, that impacts things. But you have a ton of players you never have any intention of putting on the major league roster, or not to the best of your knowledge. So the win percentage in the beginning in preseason doesn't tell you that much about the win season afterwards. But let's tell you a little bit about that. So, so suppose you were gonna, now we're down to here. Suppose you were gonna pick a baseball team at random and predict how well they'll do during the regular season. What would you predict for their win percentage? It's just some random team, and you say, well, they'll win half their games. If I don't know anything else, they'll win half, and that's the best prediction you can make. Funny thing about baseball, they don't say they call it win percent, but so you think 50%, but they don't call it that in baseball. They make it a decimal instead. So you go, oh, that's weird. That's not a percent anymore, but it's just how they do it. And then not only that, just to mess with us a little more, they make it. They write 3 decimal places, so it's almost like a per thousandth or something. I don't know. It's they call it win percent, but that's how they'll write it. So that's a win percent of 500 means you're winning half your games. Okay, suppose a team had a great preseason, just a phenomenal preseason. They were fantastic, and they won 70% of their games. They had a win percentage of 700. What does that tell you, and what would you predict? And what if they lost every game in the preseason? Would you predict that they do as badly, that they lose every game in the regular season? I'm going to pause it and give you a chance to think about it, and then I'll tell you what I think. It doesn't help unless you pause it. But that still made it feel like a pause to me, so it felt better. And so what I'd hope you'd look at this and say, well, if they won 70% of their games, that's pretty good. I mean, so there's a decent chance that they're better. Chance they're good. Right? You don't expect them to necessarily win 70% of their games in the regular season, but it's like, oh, that's a lot of games. I mean, on average, they're probably better than average. Like, they're better. Knowing that information gives you more confidence than if you knew nothing. And what if they lost every game in the preseason? They lost every single one. So first, would you predict that they do as badly? And you say, well, no, I wouldn't predict they do as badly. But they're probably bad. They're probably bad, but not that bad. Bad, but not that bad. And that's what I'd want you to take away from that. Yeah. So this is the point. So given information about X, given no information about X, or if the correlation is 0, then we'll predict the Y to be the mean. So the predicted Z-score for Ys, if the correlation is 0, then the prediction Z-score for Ys is going to be just whatever the mean is. I'll say mu, which whatever the average is. The predicted Z-score would be 0. That's the Z-score. Z-score is 0 right in the middle. If there's perfect correlation, so if R is equal to 1, then we'll predict the Z-scores of the Ys. So the Z-scores of the Ys, predicted one, will just be whatever the Z-score is of the X's. That was the looking at height. If they're one standard deviation above in X's, there'll be one standard deviation above in Y's. And if it's somewhere in between, then we predict that the Y's to be relatively closer to the mean than the X's. I mean, so if there's some correlation, like this is looking at this third example. So looking at this example here with Major League Baseball, is that there's some correlation. So I think that information gives me information. Like knowing they won a ton of games makes me feel better, and they're probably better than average. Knowing they lost every single game is also that I think they're going to be worse than average, but just they're not going to be as bad or as good as their preseason results were, or at least that's not going to be my prediction. So I'm going to predict they're going to be closer to the mean than they did in the preseason. Not at the mean, but a little bit off. Okay, I'm going to pause it here because it's time for video